Okie dokie, so for those at home, and I do hope you're going to be able to watch this before Monday, we've just differentiated a couple of things. There's a reason for that. Today we are talking about solving differential equations. Sounds really complicated. It does get really complicated beyond A level, but actually at R level it's not too bad at all. It's a very pompous way of saying what the second purpose of integration is. So the first there are two main purposes of integration. One is to find area under curves. The other is to undo dy by dx. So if we have a dy by dx, or actually I'm going to use a dh by dt. So this is the rate at which the height of something is changing, and it is proportional to the t squared. That is a differential equation. And solving that differential equation just means integrating it. And we increase the power divided by the new power. Good morning, good morning. Thank you for making it in. It's all a bit confusing because the lesson wasn't on and now the lesson is on, and but we've only just started as a result, so it's all good. So, integration undoes differentiation, and we've done that last year, and there's nothing new there. All that's new is we're now referring to this as a differential equation, and in this case, dh by dt, if h is height, is the rate at which something is changing. So that's all good. I don't need to teach you anything new in order to solve that differential equation. This is referred to as a general solution because the presence of this constant means we don't actually know, we haven't got a formula linking h and t. And of course that's going to persist until we're given a pair of values. So we might be told that when t is 0, h is something like 5. And we can substitute those values in. 4 times 0 squared, cubed, 0 divided by 3, so yes, so h 5. I'm replacing h with 5, t is 0, so we get that. So I can rewrite my general solution. And that is called a particular solution. So the first thing you need to look at when you're dealing with a differential equation question is, are they after a general solution, in which case there'll be constants, or are they after a particular solution, in which case there are no constants, and therefore you need to go hunting in the question for a pair of values you can substitute in order to find. In order to solve this differential equation, we just need to integrate once, because this is dh by dt. Therefore, it's referred to as a first-order differential equation. It's the only sort that we meet at A level. But if they had given us d2h by dt squared, we would have had to integrate twice. And we have come across that in mechanics, where if we start with acceleration and we want to know displacement, we integrate twice. That's referred to as a second-order differential equation. Let me give you another first-order differential equation. There is an issue with this differential equation. Can we see what the issue is with this differential equation? Thank you.
In terms of h.
Yeah, this statement here says the rate of change of h with respect to t. But this has h as the variable. So if we were to integrate this with respect to t, that would be like a constant. So when we are faced with a differential equation, I always say, if it's in terms of t, and we've got a t there, then Happy? If it's in respect to t, but that's in terms of h, how do we turn a frown into a smile? We just turn it upside down. So I'm going to turn this upside down. I'm going to find the reciprocal on both sides. And now, this is in respect of h, and that's h. So all of a sudden, my frown has turned into a smile. And it might be easier, in terms of differentiating, to write this as h to the minus a half over 4, perhaps. If we write that as h to the minus a half over 4, I'm hoping we can then integrate it. Go on, see if you can integrate it to get a general solution. We'll stick with the general solution of this one, so we'll have a plus c in there. So I'm going to increase the power, divide by the new power. I'm already dividing by 4, so I'm dividing by a half times 4. So that's that, which I could write as or root h over 2, or, you know. So solving differential equations is just a pompous way of saying undoing differentiation by integrating. And we've just got to be a little bit careful about the variables. This tells us what the variable is, so it needs to be in terms of that. So in this case, I need to flip it over. Now that's all well and good. I don't think we've sort of learned anything particularly new, apart from maybe a few new terms like differential equation, general solution, particular solution. Let me present you with the sort of differential equation that we are by far the most likely to encounter. So Arthur, can you see the problem with this one? Absolutely. My variable is x, but this I've got x and I've got y. What on earth is going on here? So in this one, I'm sort of not happy or sad, I'm just a bit sort of puzzled. and this is by far the most common sort of differential equation, and we need a different technique to solve this. We can't just integrate it, because we've got here the rate at which something is changing. That's nearly always what a dy by dx is telling us. The gradient of a curve is the rate at which something is changing, and it's related to the two variables. So what we do is this. We separate the variables. I mean, you know that we are used to, in questions where we perhaps want to change the subject of an equation, we're used to collecting everything with an x on one side and everything without an x on the other side. Well, we do something a little bit similar. So I've got dy here. I'm going to leave that there. I'm going to multiply both sides by dx. So that's going to appear over here. I then want everything with a y on this side, because on this side y is my variable, and I want everything with an x on this side. So this and this can stay where they are. And that has to come over here. I've got to divide both sides by tan y, so I'm left with that. And then what we do is we integrate both sides separately. And this process is referred to as separating the variables. And it's the first step in general of any differential equation question. You sometimes get ones which have a single variable, like my first two examples, but in the vast majority of situations, you're going to get one like this, where you've got to start by separating the variables. And we, therefore, are going to have to do two integrations. Now, both of these fall into the how on earth am I going to integrate that category. So I'm going to go through my normal process. 1 over tan, well, that's cot y. So I'm hoping that somewhere I'll find a way of integrating cot y. Good morning. Thank you so much for answering the call. I'm sorry if you were enjoying a lovely lion, and if you were watching the cricket, then I've done you a favour, because that's just a nightmare. So I'm hoping that you can find out a way of integrating that, and you'll find out a way of integrating that maybe by sort of casting your eye around the classroom and thinking if there's anything around the classroom that might help you. So let me give you a little chance to think about how you do that. Okay, so the differential of cot y from the formula book, from page 7 on the formula book, is ln of sine y. There's no k in there, there's no multiplier, so that's going to become remembering that and the integral of x over 1 plus x squared we came across in the starter. It's one of those, this looks a bit like what you get when you differentiate this, which means it's probably a log one, and so that's why we did that starter. So that's going to be a half of ln 1 plus x squared. Now, at this point we might be thinking, I've forgotten something, or maybe I've forgotten two things. Because surely we should have a plus c here, and we should have a plus c here, and you're right. Both of those integrations would have a constant associated with them. So but what we tend to do is we tend to roll those into a single constant, and write this as plus c. But actually, in this case, and this is quite an important subtle issue, everything else is in terms of logs. So it might be a bit easier to write that constant as the log of a value. I mean, any number can be written as ln of something, so that might be helpful, and in fact it is, because what I can then do is I can, I'm going to leave that as it is, I'm going to write this as ln of the square root of that, because that's the power of a half. And then I'm going to combine those two. The ln of a plus the ln of b is the same as the ln of ab. And then I can just unlog both sides. So we get sine y equals k. And that is as far as this particular exercise takes it. Now, these are a nightmare to mark, because this is correct. This is a general solution. There's absolutely nothing wrong with that. So, do I need to do all that rigmarole? Well, I guess in an exam they will probably be a bit more careful, and it might even be a show that question to get you to sort of get it into a particular form. But it's certainly worth remembering that we've got this option of replacing your c with ln k, which means if everything else is in terms of logs, you can sort of roll it all together. Okay, can I get you to try a similar example? So this one. And while you do that, for no reason other than just for kicks, I'm going to do a little partial fraction question over here on my own, which may or may not be helpful. We've got the issue of what do we do with the -3? And the answer to that question is we do whatever's most convenient, and actually wherever we deal with it, it will get the right answer. So I'm going to leave the -3 where it is, along with the x's. So when I separate my variables, I'm going to divide by my y minus 2, and then leave it like that. Now if you took the -3 down, that's not a disaster at all, but actually it works out quite nicely because I've partial fractioned that for you, and that becomes so we've got three things that are going to turn into logs. So the first, the left-hand side, the dy is going to turn into an ln, and then you're going to have an ln here, an ln here, and therefore it probably is going to make sense to write your constant in terms of ln. So go on, see if you can end up in this example with a y equals equation. So see if we can get it as far as y equals. So this becomes, and please watch closely because I'm very likely to make a mistake here with all this lning going on. That becomes that. This becomes -2 ln of 2x plus 1 divided by what you get when you differentiate the bracket. So I think that gives me which is 2, so that just gives me -1 lot of that. That gives me ln of x plus 2, and then there's a plus c, which I'm going to write as ln of k. And do you remember we did this? So the left-hand side can just stay like that for now. So what I'm going to do is roll those two together, and then write it as that, take away that. So what you actually get is k times x plus 2 over 2x plus 1. And then I'm going to unlog both sides. That's bad maths. What I've done is I've taken e to the power of both sides, and then I'm just going to add 2. Now is that what they get? Right. Oh, they had a condition. Right, okay. So at this point, right, okay, now I'm going to write it like this. General solution. At this point in the question it says, oh, by the way, when x equals 1, y equals 4. So I can then say, right, so 4 equals 3k over 3, that's good, plus 2, so that means 4 equals k plus 2, so k is 2. So I end up with y equals 2 Bob's your uncle, general solution. Okay, so I would suggest these. Can I just point out that for part D, there's a funny E expression in part D, isn't there? Yes, so E, in part D you've got an E to the x minus y, which is the same as that, isn't it? E to the x divided by e to the y, because when you are dividing powers of the same thing, you subtract the indices. So I think when you get to D, it makes it a bit easier to write it like that. Have a go. And if those of you at home can at least have a go at number 1, A, B and D, that would be just peachy ahead of Monday. So I'm going to, this is the first one, which is a little bit more straightforward. The left-hand side becomes a log. The right-hand side is just something we can integrate as normal. Minus 2x squared over 2 is just minus x squared. And I'm going to do it in two ways. I'm going to, and the question says write it as y equals. So one thing I can do is undo ln, which we do by doing e to the power of. So I would have e to the power of x plus c, and then I could take away 1 from that. Sorry, so we want to in the power. Given and that's a general solution because sorry, that's not plus 1, that's plus c, sorry. So that's one way we could write the answer, nothing wrong with that at all. Another way of writing the answer would be to write the constant as an ln, like we have been doing. So there's nothing wrong with that. I want to be absolutely clear, there's nothing wrong with that. So the other way, I'm going to oh no. Come back. Oh, what have I done? Is it gone altogether? Right, okay. I'm going to pause the camera and come back in a minute. Here we are again, as if nothing had ever happened. Right, so what I'm going to do this time is I'm going to put the constant over here and write it as an ln. That constant can go anywhere we want, all right? And this is why these are a nightmare to mark, because the thing we just wrote is perfectly okay. But if we write it like that, then we've got ln of k times 1 plus y. And when we then do that, we're going to have, I'm going to divide that by k, which I'm going to write like that. And then we take away the 1. So we end up with the same, an alternative version of that solution, either of which are fine. These differential equations are always a bit fiddly at the end. They're sort of unsatisfying at the end.